This is lesson 2 from chapter 15 on reaction kinetics and reaction mechanism, the two essential points that are elaborated and expounded upon in this chapter. Today we're going to be looking at the effect of concentration on reaction rate. In other words, when we change the concentration, often that's usually molarity, how does that affect the speed at which the reaction changes? So the reaction rate is probably going to be measured in the change in molarity divided by the change in time, though sometimes you can talk about the change in pressure divided by the change in time if you're working with gases. And this information helps us to learn something about the mechanism. The mechanism is different from the rate, but the rate gives us clues as to what's going on when the particles actually collide with each other, even though we can't visibly see them or even computer model them, at least yet. By the way, as we concentrate on the effect of concentration, pardon the pun, we need to hold all other variables constant. So this is assuming that the temperature does not change during the course of the experiment, during the course of the reaction. And that's not as easy to do sometimes as you might think. All right, so let's take a look. We have four possibilities here. When we change the concentration, let's say that we double the concentration of dinitrogen pentoxide. Does that make the rate go faster, slower, or not change? And in this particular reaction, we would see that doubling the concentration doubles the rate. And you'd have to see this in a data table of the experimental results to prove this. In other words, they are directly proportional. Obviously, things can be proportional. For example, if you have a curve that goes like this, that's proportional. But when you have a curve that has a straight line, that's directly proportional, a linear relationship as opposed to an exponential relationship. So when they are directly proportional, it means doubling or tripling the one thing doubles or triples the other thing. You could also go the other direction. If you cut the concentration in half, you would cut the rate in half. Notice the symbol that we're using here for being proportional. Now, another possibility is that you could change the concentration of your reactants and it doesn't change the rate at all. In other words, we would say that the rate is independent of what the concentration happens to be. A third possibility, which is also pretty common, is if you double the concentration of the reactants, you might actually have the rate go 4 times greater, 2 squared, in which case you're going to have this kind of curve. If you were graphing it, it's going to be exponential. Now, it is possible to get higher orders of magnitude in the exponent than a 2, but very, very unusual. And then finally, we have to keep in mind the interesting fact that sometimes the concentration of the catalyst can affect the rate of the reaction, even though the catalyst is not actually used up during the course of the reaction. Now, when we do experiments to see what the effect of changing the concentration is on the reaction rate, we can use that information to create what we call a reaction rate equation or a rate law. This law is going to be a law that governs this particular reaction at this particular temperature. So it's a very exclusive, specific kind of rate law. It's not like the law of gravity that we believe to be universally true. So when we did our experiment, or if we imagined the experiment previously, we would say that if we doubled the concentration of my dinitrogen pentoxide and it caused the rate of my reaction to become twice as much, that is a linear relationship. In other words, if I multiplied this molarity by 2, it caused this to increase by 2. And therefore, we would have an exponent of 1 for the molarity of my dinitrogen pentoxide in the reaction rate law. So my reaction rate law would end up being the rate of my reaction equals my proportionality constant times the concentration of my dinitrogen pentoxide to the first power. And of course, you don't need to write the number 1. That would be understood when you don't have an exponent there. The value of K is the rate constant. And again, this value of K is going to depend upon each individual reaction. Generically, it looks like this. If I have A moles of reactant capital A and B moles of reactant capital B, let's say I produce X moles of product capital X. So this would be a composition reaction where 2 reactants become 1. In any case, the generic rate law then would be my reaction rate, we could just call that R, is going to be the molarity of my first reactant raised to some power m times the molarity of my second reactant raised to some power n, and we need our constant. Now you'll notice that even though I have coefficients of lowercase a and lowercase b, my exponents are not a and b. Many times you're going to find that the coefficient actually becomes the exponent, but that is not a rule. Later on, when we talk about equilibrium reactions, then the exponents are whatever the coefficients were in the balanced equation. But that is in equilibrium expressions. That is not true here. Here you have to remember that your coefficients do not automatically become the exponents in the reaction. That is a fundamental difference between this chapter and the chapters on equilibrium to come. Don't get that mixed up. So even though M and N might have the same values as A and B, it's not uncommon, don't assume it to be a rule. Now the exponents in this equation are usually positive. Sometimes they can be negative. They can even be fractions, or if they're independent, it can be 0. They have no effect. But the main point is you do not know from the balanced equation. You have to do an experiment. In your equilibrium expressions, you know what the equilibrium expression is by simply looking at the balanced equation. But when it comes to writing a reaction rate law, you have to look at the experimental data. You can't just automatically look only at the balanced equation. Very important to know that. Now, whatever that coefficient is, the exponent is, we often call that the order. You can have the order with respect to one reactant, the order with respect to another reactant, if there is one, and then you can have the overall order, which is going to be the sum of the individual exponents of each of the reactants that you have in the equation. So the order of a reaction is going to be the sum of the exponents. So if I'm looking at this equation right here, and we determine, coming over to this page, we first of all need to determine what is the exponent for reactant nitrogen monoxide and the reactant chlorine gas. Now here they already jumped to the conclusion it's a 2 and a 1. So we would say that this reaction is second order with respect to nitrogen monoxide, it is first order with respect to chlorine gas, and it's third order overall because we add those two together. But let's see where they got the exponents of a 2 and a 1. So we look at the experimental data. You always have to do this. And these are kind of fun. And you're looking for two experiments where one of the reactants' molarities is held constant. So for example, in experiment 1 and experiment 2, you'll notice that we double the concentration of nitrogen monoxide. But the reason I looked at experiment 1 and 2 was because the other variables being held constant. There is no change. So when I double the molarity of the one reactant, I come over here and look at how does the rate change, and you'll notice that the rate changes by a factor of 4. We've got to multiply by 4 to get the new rate. So how do I come up with a 4? Well, 4 is 2 squared. So that's where this 2 comes from that we see up here. It's second order with respect to nitrogen monoxide. Now, let's pick a different color, and let's go after, find another 2 experiments where this time we hold the nitrogen monoxide constant. So if you look here, for example, I'm holding the nitrogen monoxide at a molarity of 0.500, but what happens to the rate in those 2 experiments? And you can see that the rate is doubled. You could also perhaps look at another experiment. What if we went from this experiment to here? The nitrogen monoxide doesn't change, so we look at the chlorine, and that gets doubled. And so when we come over here to look at what the effect on the rate is, it's doubled, so it's consistent, as it should be. So when we doubled the molarity of chlorine, it doubled the rate, giving me an exponent of 1. So my reaction is first order with respect to chlorine. And again, don't forget, in some experiments, you might get a 0 order if the concentration does not affect the reaction rate, meaning that the reaction rate is independent of the concentration of your reactant. All right, now let's continue to show you the value of knowing a reaction rate law. Now we need to find what is that value of K. How do we calculate what that value of K is? Well, if you think about it, once we have determined what the reaction rate is for different molarities of my reactants, and we've determined what the exponents in the rate law are, in this case you can see that I have I don't worry about water, so my main reactant is right there, and you can see that in this, they're assuming the data is correct, and they analyzed it correctly, and they came up with first order with respect to this compound. In any case, once we know what the correct rate law is, that my rate equals K times molarity times first order, now what I need to do is pick any one of my experiments data. You might have 2, 3, 4, 5, or 6 different experiments where you varied the concentration of the reactant or reactants to see what the effect would be on the rate, and pick any one of those experiments because your rate law should be true for all of them. And pick any one of those experiments, you plug your data in, and you solve it for K. And if your rate law is correct, and if you do your math correctly, no matter which experiment you choose, every single time you'll get the same value of K. K will be a constant for that particular reaction at that particular temperature. So once you find the value of K, now you can use that to predict what will be the reaction rate at any molarity you want of any reactant you want. And vice versa, if you want to have a particular rate, if there's a particular rate you need or are looking for in the research or the process that you are working on, then you can see what the molarity has to be to give you that rate. This all means you know what the value of K is. Now, by the way, the value of K is going to have different units depending upon the situation. For example, in the first order reaction, my rate is going to equal some value of K times the molarity of my, let's just use a reaction that only has one reactant for the sake of simplicity, and it's first order, okay? That means that we're saying that my moles per liter, that's my molarity, per time, that's the units of rate, equal K times the units of molarity, which are moles per liter. So what are the units of K going to be? Well, my moles cancel, the liters cancel, and you can see that K equals 1 over time for a first order reaction. All right, let's erase that and let's look at another situation. In this case, we are going to say, what about a second order reaction? What if my rate equals the K times the molarity of my reactant and its second order? That would mean that my moles per liter, which is molarity, divided by time, because it's a rate, equals K times my moles per liter squared. And when you solve for K this time, you can see that moles cancel. One of the moles on the right then will cancel. One of the liters cancel. And you can see that when you solve this for K, you're going to end up getting, the time stays in the denominator. This mole is going to go downstairs on the other side. The liters will go upstairs on the other side. And you're going to get these units for a second order reaction. Notice that the units change from first order to second order for your K constant. So let's erase all of this and let's do the last one. In the last one, what if we have a zero order reaction? In other words, what if my rate equals K times my molarity to the 0 power? Well, anything to the 0 power is 1, which means my rate equals K, which means my units of K are going to be the same as the units of R, which is moles per liter per time. Now let's do some examples. Here you have some methyl acetate. You'll remember that's an ester. And esters are made when you add an acid to an alcohol. Well, here we have just the opposite. Here we have my methyl acetate breaking down to become an acid and an alcohol. And my acid is going to be acetic acid. And so in the name of the ester which it would make, or which it would come from, is acetate. And the alcohol would be methyl alcohol, a 1-carbon alcohol. And that gives us the first name of my ester, if you remember your organic chemistry. So in this particular reaction, methyl acetate in a basic solution will yield us a mixture of an acid and an alcohol. And so that explains that reaction. And so we come down here, we're going to do 3 experiments. And you'll notice that here are my 2 reactants. Here's reactant number 1, reactant number 2. And of course, the letter R could stand for reactant. It could also stand for rate. So you got to keep this all straight. And I'll erase that so we don't get confused. And so what you'll notice when I do 3 experiments, I'm looking for an experiment where the molarity of one of my reactants is not changed. And you'll notice here, I'm holding the molarity of the methyl acetate constant. And I'm doubling the molarity of the base, sodium hydroxide, potassium hydroxide, whatever sodium or potassium would be a spectator ion. What effect does that have on the rate? Well, it doubles the rate. We could also say, well, let's hold the concentration of hydroxide constant. I'll go to a different color. Here, the concentration of hydroxide is being held constant, and now we're going to double the molarity or concentration of my methyl acetate. What effect does that have on the rate? That also doubles it. That means that in the rate law, my rate is going to equal some constant times the molarity of my methyl acetate to the first power and the molarity of my hydroxide, sodium or potassium hydroxide, also to the first power. So my reaction is first order with respect to methyl acetate, first order with respect to the hydroxide, and overall, it's going to be a second order reaction. So the next thing I'm going to do is pick an experiment. You can pick experiment 1, experiment 2, experiment 3, doesn't matter. Put those numbers that you have in the experiment into your 3 slots. Solve this for K. If you're not quite sure you did it right, plug in the values of a second experiment. And if you both did the math right and you have the correct rate law, you should get the same value of K every time. And in this case, your value of K is 0.14 liter per mole second, because it's second order. Here's another experiment we can do. We have lots of options here. And when we look at holding something constant, here's where we're holding the carbon monoxide concentration constant. We're doubling the nitrogen dioxide. It doubles this, so we know that doubling the molarity doubles the rate, so it's going to be first order with respect to nitrogen dioxide. We could check that in some other places as well. Let's see, we might want to look down here I'm looking for some other places to check. Let's say we go from here to here. No, I don't want to do that one. So I'm going to erase that. I need to find a place where I'm holding the molarity of my nitrogen monoxide constant. So let's look at this one. So if I hold it constant, say we're going from here to here, I'm holding the nitrogen dioxide constant, and then when I go from here to here, you'll notice that this causes a doubling. Notice the exponent, -4, -3, so we're doubling. This is times 2. It doubles the rate. So again, it's first order with respect to carbon monoxide as well. Now, all of this right here, in my mind, is a little bit too much work to get the result that I just did. And that it's first order with respect to both molarities of carbon monoxide and nitrogen dioxide. Now that I have my rate law, my rate equals K times that, I can pick any one of those experiments, plug it in, solve for K. Now, once I know what K is, I can use that to predict what molarity I might need to acquire a certain rate, or what rate I should expect if I choose some molarities that I didn't do any experiments on. I could predict what it would be. Here's another example for you. Just looking down here, if here we're quadrupling the molarity or cutting the molarity of nitrogen monoxide by 4, and you can see that this also reduces it by a factor of 4. I'm sorry, by a factor of 16. You could also look at it this way. Going from here to here, you're going times 4. Going from here to here, it's times 16. So you know that this is going to be second order with respect to your nitrogen monoxide. Here's another example. Using the rate equation and the rate constant that we already found in a previous example. So given the correct rate law right here, which is first order with respect to each reactant, and given the value of K, this is also given, which right there, can we make a prediction? It says determine the rate of the reaction that we should expect if we have this molarity of carbon monoxide, this molarity of nitrogen dioxide. Just plug it in and we predict this should be the rate. And we could test that prediction, but God's creation is generally very, very consistent, for an ironic understatement. And that concludes some examples on reaction rate laws, how to determine them, and how to use them.